Okay, we're going to solve this differential equation. So you can see here we've got a second order linear non-homogeneous differential equation with dependent variable y and independent variable t and a couple of initial conditions. So we've actually talked about some other methods that we know for how to solve this one. So you could use a characteristic polynomial since you have constant functions for the coefficients for the y terms. You could use a characteristic polynomial and then use undetermined coefficients or variation of parameters. Undetermined coefficients is easier to find the solution for this. But the goal here in this example is not exactly just to find the solution, but to practice a little bit using Laplace transforms. So we're going to solve this one using Laplace transforms, not because that's the best method for this problem. If you don't have to practice Laplace transforms, I would not choose this method. But we're going to practice the method of Laplace transforms so that when we get to harder problems where we actually need Laplace transforms, we know how it works, right? So we're going to do it with an easier problem before we get to the crazy ones. All right, so when we do Laplace transforms, remember, first step is you're going to just take the Laplace transform of both sides of the equation. So doing the same thing to both sides of the equation. And then remember that the Laplace transform has that linearity property, which allows you to chunk things term by term and factor constants out. So I'm going to skip a step and go right to that step where I've taken the Laplace transform of the left side. So I'll have the Laplace transform of y double prime. And then instead of the whole left side here, I've chunked this term by term. I've used part of that linearity property. And then I'm going to pull the 3 out, plus the Laplace transform of y prime, plus 2 times the Laplace transform of y. And then that should equal the Laplace transform of t. Okay, so Laplace transform of both sides of the equation. Second main step that you want to do here, change to a marker that writes a little better. Second main step that you want to do here then is to use your table of Laplace transforms to actually find the Laplace transform of each side of the equation. So for the left side, after you've done a few of these problems, you should be pretty good at doing that. But you may not be there yet. So on that table of Laplace transforms that you have, you're looking up, for this one, it's number 23 on this table that I provided you in the packet, the Laplace transform for the second derivative. So that's what I'm doing here. So it says we've got s squared, and then on my table it says capital F of s. But remember here we've got y as our dependent variable, not f. So we'll have capital Y of s. I don't usually write the of s because that gets a little confusing in the notation. So s squared y, and then it says minus s times little f of 0. So here are my dependent variables y, not f. So little y of 0. Remember that the capital Y and the lowercase y have different meanings. The capital Y is the Laplace transform of the function little y. That's up there at the top of your chart, kind of in those headings. And then minus little f prime of 0. So we'll have little y prime of 0. All right, so all of that is from the Laplace transform of y double prime. And then I'm going to have plus 3 times Laplace transform of y prime. So that's number 22 in your chart here. So s, and then it says capital F of s. So our dependent variable, though, is y. So y of s. I'm not going to write the of s. Again, capital Y. So again, make sure you're distinguishing between those capital and lowercase variables there. And then minus little f of 0. So minus little y of 0. Right, so that is from this second term on the left side. And then plus 2. And then, sometimes students get stuck here. They don't know where to look on this chart. So this, remember that y is our dependent variable. What we're trying to find here at the end is some function little y of t. And so just in the generic notation, when you're taking Laplace transform of a function, we use the capital letter to designate that. So that's what those capital y's represent throughout here, is the Laplace transform of this function lowercase y. Equals, all right, so that doesn't mean capital S here. Remember, for the independent variable, the Laplace transform of that independent variable is a function of s, right? So t, that's number 2 here on my chart. Laplace transform of lowercase t is 1 over s squared. And again, remember, all of these Laplace transforms in this chart come from using that definition of the Laplace transform. It's an improper integral, and so you evaluate it, do the limits, and then that's what falls out. All right, so there I've taken the Laplace transform of both sides of the equation. The next thing I want to do is go ahead and sub in my initial conditions. I've got y of 0 in a couple places and y prime of 0 that I can plug in. So I'm going to go ahead and simplify after I substitute in those. This term will go away because y of 0 is 0. And then y prime of 0 is 2. And then here, y of 0 is 0. So this will just be 3s times capital Y plus 2 times capital Y equals 1 over s squared. Okay, so I took the Laplace transform of both sides. I substituted in my initial conditions. Now the next step is you want to get prepared to do that inverse Laplace transform. So in order to do that, you need to solve for capital Y and then maybe do some algebraic manipulation so you can use your chart to do those inverse Laplace transforms. All right, so I'm going to add 2 to both sides of the equation, and I'm going to just cross this off here and put a plus 2 over here to do that. And then I'm going to factor out a y and divide through by the factor that's left. When I do that, I'm going to end up having to do some partial fractions. To make life easier on myself, I'm going to go ahead and combine this into a single fraction. Otherwise, you're going to have more partial fractions problems to do than you otherwise would. So I can think of this 2 as 2s squared over s squared. So this right-hand side could be rewritten as 1 plus 2s squared, the whole thing over s squared. You don't have to do that simplification step, but that's my advice, because then it's going to give you less work to do later when you're doing the complicated, possibly complicated partial fractions step. Okay, so over here on the left side, I'm going to factor out my capital Y, and I'm going to end up dividing through by what is left, which will be this polynomial involving s. And I have this simplified version over here. When you do that, you're going to want this eventually to be factored if it factors more so that we can do that partial fraction. So I'm going to, as I divide through by this, I'm going to notice that this s squared plus 3s plus 2 can be rewritten as s plus 2 times s plus 1. Okay, so solving for capital Y. So again, this factors into s plus 2 times s plus 1. Okay, so again, the whole idea with Laplace transforms is that you start with some differential equation that, for whatever reason, our other methods don't work for. Remember that this one our other methods would have worked for, but we're going to get to some where that wouldn't happen. You take the Laplace transform of both sides, you do algebra to solve for y, and then you do the inverse Laplace transform, which takes you back into this domain involving lowercase y's and t's. So at this point, you're going to use your table to find the inverse Laplace transform of this. But the issue is this is nowhere on that table. There's nothing like that form on your table. So what you want to do is use whatever algebra is appropriate to break this apart into expressions that are on your table. And remembering that the Laplace transform and the inverse Laplace transform have those linearity properties. So you can break them apart term by term, like we did here, and you can factor out constants like we did here, both with the Laplace transform and the inverse Laplace transform. Okay, so to simplify this and break this apart into forms that will work with what's on my table here, I'm going to need to do some partial fractions. So this isn't a terribly complicated partial fractions problem. I'm going to set it up and skip a little bit of algebra just to save some space over here. But the setup is generally the hard step for students for this. So I have these two factors here that are distinct linear factors. And then this s squared is sometimes what is tricky for students. This is a repeated linear factor. So it is just like a factor of s, but with multiplicity 2. So when I set that partial fractions up, because all of my factors on the denominator are really linear factors, even though this one has multiplicity 2, it's still a linear factor, the numerators are all just going to be constants. So that makes it a little bit easier than if I had irreducible quadratic factors. We will look at an example like that in the next one. All right, so it doesn't matter what order you write these in, but I'm going to have this unknown constant a over s, and then another constant over s squared. Remember, you count up. You have terms that count up to whatever this multiplicity is. So if I had s cubed here, I would have s squared, s cubed. And then I need one fraction for each of these factors as well. And that's going to be equal to my expression here. All right, and then this goes back to the partial fraction stuff that you did in algebra, or we used it in Calc 2 for integration. So you're going to multiply through by that common denominator, which is s squared times s plus 1 times s plus 2. Write down what you have left, and then figure out what those constants are. So I'm multiplying through by this common denominator. When I do that on this first fraction, this s cancels with one of the s's. So I'm left with a s, s plus 1, s plus 2. When I multiply through on this second term, the s squared will cancel with what I'm multiplying through by. So I'll be left with b times s plus 1 times s plus 2. The c, when I multiply through by this denominator, the s plus 2 will cancel. So I'll be left with c times these other factors. And then for the last one here, the d, the s plus 1 factor will cancel. All right, so I have all of that is going to be equal to 1 plus 2s squared. Okay, so then you have a couple methods when you do these partial fractions problems for handling, figuring out what the constants are. One is you can set up a system of equations with coefficients of like terms. We reviewed this at the beginning of the semester when we did all that review stuff. It might have been a while. Maybe you need to go back and look at that. I'm going to write down the system of equations that you would get here. The other method that we talked about is substituting in convenient values of s, which will make things drop out, and that allows you to find at least some of these constants a, b, c, d. All right, so I'm going to think about the system of equations here, and I'm going to go ahead and write that down and use that method. All right, so for the s cubed terms, s cubed is the highest power term that I'm going to have over here. I'll have an as cubed when I multiply all of this out. I won't have any s cubed terms here. I'll have a c s cubed, a d s cubed, and I have 0 s cubed on the right-hand side of the equation. For s squared terms, you want to be a little careful about that. When you multiply this out, you'll have a 3s squared on the middle here. When you multiply all this out, times a. Over here, you'll have an s squared times b. Here we'll have a c s squared and a 2d s squared, and that's going to equal to this coefficient on the right-hand side for the s squared terms. For the s terms, when I FOIL all this out, I'll have a 2s from all of this, so a times 2s. So 2a is the coefficient for the s term. Here I'll have a 2s plus a 1s, so 3s times b. So 3b. There's no s term here and no s term here. And the right-hand side, there's no s term, so that coefficient is 0. And then the constant terms. On the left side, there won't be any constant terms from this a part here. From the b part, I'll have a 2b. And then that's it. I won't have any constant terms here for these. And so then on the right-hand side, I get 1. Okay, so then you've got a system of equations to solve. B falls right out. Once you find B, you can put that in to find A. You can put those in. You've got a system of equations in 2 variables. You can solve that. Or you can use your matrix feature on your calculator to solve this system of equations. So I am just going to look over here on my scratch paper and write down what all we have. So let's see, I've got a equals -3/4. B was, oh, right here, 1/2. C is -9/4. And D is 3. This is sometimes where it's really easy to make a mistake. When you're doing my math lab homework, it can be incredibly frustrating if you've made a little mistake here, and then you put that back in, you do your inverse Laplace transform, you type your answer into my math lab, and it says wrong. And it's hard to figure out where your mistake is. This would be the first place I check. This is easy to make a mistake in that algebra there. All right, but once I put those back in, then it's a matter of actually doing the Laplace transform part of the problem. So I'm going to put these constants in here. I'm going to rewrite this left side. I'm going to rewrite the right side of this equation the way it should be. I'm going to put my constants, instead of on a fraction on top of a fraction, I'll put that out front. So I'll have -3/4 times 1/s, and then plus 1/2 times 1/s squared, and then minus 9/4 times 1/s plus 2, and plus 3 times 1/s plus 1. Okay, so all this algebra work over here for the partial fractions was basically to break this apart so that all of these expressions are in the form of things that we have known inverse Laplace transforms for, so that we don't have to go back to that definition to figure those out. So all of these expressions here are in your table of Laplace transforms, and then when you go back to the other column, you're doing the inverse Laplace transform. All right, so now the step is going to be that I'm going to do the inverse Laplace transform of both sides of the equation. So when I do the inverse Laplace transform, that takes me back to my little y and t domain, from capital Y and S back to little y and t. So the inverse Laplace transform of capital Y is lowercase y. My -3/4, remember you can pull the constants out and do this term by term. All right, so this I'm going to look up in my little chart. That's the first one here. Inverse Laplace transform of 1/s is 1. So 1. And then 1/s squared, that's the second one in your chart. Inverse Laplace transform of 1/s squared is t. After you've done a bunch of these problems, you'll probably have some of these memorized. That's perfectly fine. You do not have to memorize them. On a test, even if I thought I had them memorized, I might look it up just to be sure that I hadn't made a mistake there. All right, these last two are of the form 1/s minus a. So what it says there in the table, it's got a 1/s minus a in the table, and then the inverse Laplace transform is e to the at. All right, so you need to be careful with the negative and be sure you're clear what the a is here. So this is number 5 on our table, and here the a is -2, and for this one the a will be -1. Same inverse Laplace transform, just with the different a. All right, so e to the -2t and 3e to the -1t. All right, so there is my particular solution that satisfies that differential equation and our initial conditions. Again, if you're given your choice of methods to solve this differential equation, this is not the method I would choose. A characteristic polynomial and undetermined coefficients is pretty fast, a lot faster than all of this mess over here. But there are problems where you will have to use Laplace transforms, so practice these using the method that it suggests so that you can get used to that and handle the harder problems when you get there.